Hey everyone, today I'll be doing the Term 1 Week 7 Physics past papers for the periodic. I'm sorry if my microphone quality is a little bit bad. It's because my headset broke, so I'm having to record through the tablet's mic. Hopefully I'll get this sorted out. Anyway, so these are the past papers that are included. We have 8 of them. They are all in this file that I've compiled, so I will be going through all of them. Now, we start off with the first question, which is actually the fourth question. State the principle of superposition. Now, the principle of superposition is something you should absolutely memorize, and it's something very, very easy to memorize. Simply, it is put as two waves. Why is it so thick? Oh, wait, why am I recording with this? Wait, it's like this. Two waves overlap. That's the first mark, okay? And then you say, and the resultant displacement is the sum of their original, or sorry, not original, right? Individual displacements. Okay, so you should memorize this. The principle of superposition is when two waves overlap, so that's the first mark. Let me mark where you get the marks. So two waves overlap, one mark. Resultant displacement is the sum of the original displacement, mark 2. So as you can see, it's 2 marks. So if it comes in written part, which I think it generally might, it's 3 marks. Don't miss out on it. You're memorizing one sentence and you get 2 marks for it, or 1, depending on how the written part is phrased. Okay, so part B, light of wavelength 7.2 times 10 to the power of negative 7 meters. So this is lambda. This here, it is lambda. Is incident normally on a double slit, as shown in figure 4.1. Light, this is the wavelength, okay. This is what we call the slit separation. This is the slit separation, right? It's the distance between the two slits. We call this either small d, or you can write A. And then this is capital D. Okay. Capital D is the distance between the slits and the screen. Okay, a screen is at a distance capital D from the double slit. The double slit and the screen are parallel. The separation of the slits in the double slit arrangement is 0.16 millimeters. Okay, that's this is D, as we said on the figure. The resulting interference pattern contains 9 dark fringes as shown in figure 4.2. First of all, let's start labeling our bright fringes. Now, this is our first bright, in the figure given, obviously, that might not be correct, but in the figure given, this is our first bright fringe, our second bright fringe, our third bright fringe, fourth, fifth, sixth, seventh, eighth. This is the 9th and this is the 0th. We're not counting them. They're not counted though. Look, they're not in the reading bar. Okay, now we can count our dark fringes. Remember, the formula for destructive or constructive is m lambda. Constructive is bright fringes. Now, destructive is m plus half lambda. Okay, now this is when the dark fringes. Okay, m is obviously belongs to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Okay, now, for the bright fringes, right, if let's label them normally. So this is our first bright fringe, second, third, fourth, fifth, sixth, seventh, eighth, ninth. However, we're not going to be using these. These are not what we're going to be using. What we're actually going to use is this formula, right? Remember, this is the 0th bright fringe in our figure. It doesn't necessarily mean that this is the central maximum. It could not be. Yani they could give us this part. Okay, but the central maximum would be somewhere here. So we're just taking it relative to the figure given, right? So this means if this is the 0th, then this is the 0.5th, this is the 1.5th, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5, and 8.5, right? Because remember, the formula is m plus half lambda. So when m equals 0 in our case here, it's going to be 0 plus half, 0.5, 0.5 lambda. So we're just going to take it as the 0.5th fringe. Okay. So now that we have these, we're not going to be using these. So for sake of confusion, let me just erase them. Okay. Now, let me put this back on. They want us to calculate D, and they told us the distance between the centers of the first and 9th dark fringes is 3.2 centimeters. Okay. Now, if you think about it, right? The 3.2 centimeters, this is the y position, this is the change, sorry, this is the change in the y positions of this dark fringe and this dark fringe, right? So we're gonna say y of, remember the formula, ym equals m lambda d over d, right? So we're gonna say y of 8.5 minus y of 0.5 is equal to 3.2 times 10 to the power of negative 2, because it's in centimeters, right? So this is the actual reading. Because look, right, if you subtract the 8.5, the y position of the 8.5 dark fringe and the 0.5 dark fringe, you're gonna get 3.2. This is the change in their y positions, right? Because remember, this is taken from the screen. And what is the ym? What do we say as ym? Ym is essentially this here. So this is the y-axis, right? At the central maximum, let's say it's here, m equals 0, right? So we're gonna have, this is as 0, right? Because the formula is ym equals m lambda d over d, right? So you have 0 here. 0 times anything will give me 0, right? Now, say the first bright fringe forms here. So m equals 1. M equals 1. So you're gonna have y1, right? We're gonna have, it's gonna be a certain number, right? y1. And then y2, or sorry, when m equals 2, you're gonna have y2, right? And then this can also go downwards. You can also have here m equals negative 1, y of negative 1, etc, etc. It continues. Now, the change of this from this, so y2 minus y1, this will give me delta y, right? This will give me the change in y, okay? Why am I saying delta y? Because we're gonna use this now, okay? Now that we have this, setup, okay? Now, let's find the expression for y of 8.5 minus y of 0.5. So, y of 8.5, so we're gonna have 8.5 lambda, which is given to me as, actually I'll just take this up here. So this goes up here. 8.5, let me put it in brackets, so I can do it on a calculator in one step. Lambda is 7.2 times 10 power of negative 7, times 7.2 times 10 power of negative 7, k times d, over 0.16 millimeters, so it's going to be 0.16 times 10 power of negative 3, right? Because remember, this was the given, this was 0.16 millimeter, this is d, minus 0.5 times 7.2 times 10 power of negative 7 times capital D over 0.16 times 10 power of negative 3. Now, why did I do this, right? Because remember what we said. We said that y of 8.5 minus y of 0.5 will give me 3.2 times 10 power of negative 2, right? So we're just going to expand. We're going to plug in this for this. We're going to substitute the formula. Now, instead of m, we're going to have 8.5, and instead of m, we're going to have 0.5. So that's essentially what I did. M lambda d over small d, m lambda d over small d, right? And this whole thing will equal 3.2 times 10 to the power of negative 7 centimeters. Now, or sorry, meters. What? Times 10 to the power of negative 7? Times 10 to the power of negative 2 meters. Okay, now do this on a calculator in one step using your equation solver, because it's a nightmare. It's a nightmare to do normally. So 8.5 times 7.2 times 10 to the power of negative 7 x over 0.16 times 10 to the power of negative 3 minus 0.5 times 7.2 times 10 to the power of negative 7 times x over 0.16 times 10 to the power of negative 3, close the bracket. Remember, you have to have the brackets under the minus. Okay, equals to 3.2 times 10 to the power of negative 2. Now on an equation solver, this will give me 0.88888 repeating meters. So d is going to equal to 0.888 repeating meters. Now, in A-level physics, you tend to round to two significant figures. So d will round to 0.89 meters, and that's my answer, 0.89 meters. Oh, the meters already given. Now, a quick note about this. The marking scheme uses something we've never been taught, unless you know the formula. The formula that they use is, I believe it was y equals ax over d. I have no idea what this formula is, and I don't really know how to use it, because again, we've never been taught it. However, these two are essentially the same, right? So you can find one from the other. but I wouldn't recommend it. Now, this graph is a little bit annoying, but you can find it. So the slit separation is now gradually decreased from 0.16 millimeter to 0.04 millimeter. The slit between the distances between the centers of adjacent dark fringes is x. On figure 4.3, sketch the variation of x with the slit separation. Okay, so for this question, I can approach it in two different ways. Now, I can first of all start by taking the easy, in my opinion. I'll explain both ways. So if you don't understand this way, just keep watching and figure out the other way. I have the formula ym, sorry, why is it in red? So ym equals to m lambda d over small d, right? And now what I'm concerned about in this formula, in this question, relating this formula, is the slit separation. So I'm only concerned with d and the variation of x, which is they told you the distance between the centers of adjacent dark fringes. So that means it's just the y, it's delta y, right? It's delta y because it's the distance between the centers. And this, by the way, essentially delta y, like if you want me to derive it mathematically, delta y is lambda d over d. Okay, this is what delta y is. So for example, in our case here, I'm not gonna go into details, but if you were to subtract this, right, this would give you 8.5 delta y minus 0.5 delta y. So you'll have 8 delta y. Then you'll divide whatever. I'm not gonna go into this. I won't. In the file, I'll send a solved past paper file. I do derive it there. And it is something very important that we will be using this later. I will use this later, and it's very, very important. Okay, there is other ways, but like it's a shortcut. Now, so this is delta y, right? Now, this is a constant, right? This will make a constant always, because I'm not changing my delta, nor am I changing the screen distance. They said that stays the same. The only thing they're changing is the where is it? They're changing the slit separation, so they're changing d, right? And consequently, the delta y will change. So essentially what I can say is delta y is proportional to 1 over d, right? Because if you know this in math, right? You know this from math. This is actually just going to say delta y is equal to k over d, which you can simplify to delta y alpha, which means proportional to 1 over d. Now, what this means for me, again, I'll explain the other way, but what this means for me is that when delta y basically doubles, okay, 1 over d will halve, right? Because they're inversely proportional. So when delta y increases, or sorry, not 1 over d, when delta y increases, d will decrease. Okay, that's what that is saying. Now, now that we know this, we have this established. Okay, I can say, for example, if delta y is gonna double by 2, then d will get halved, right? So, and if you look here, these are all multiples of 0.04. So this is double, this is triple, and this is quadruple, right? So I technically just need one value, which is this value here. If the easiest value for me will be the 0.04, right? If I find how much is the slit separation at 0.04, it's very, very easy. So what we're gonna do is we're gonna plug in 0.04 for d, and we have delta lambda d. So lambda d, remember lambda is 7.2 times 10 to the power of negative 7, and d we found it to be 0.89. Right? Now, small d, we just said it is going to be 0.04. So 0.04 gives me 1.602 times 10 to the power of negative 5. Oh wait, sorry, I forgot, times 10 to the power of negative 3. This is 0.04 millimeters, right? So you're going to do 0.04 times 10 to the power of negative 3, which gives me 0.01602. However, this is in meters. Look at what x is. X again is the distance between this, what we just calculated now, 0.016. This is x, but that's x in meters. They want it in centimeters. So what we're going to do is we're going to do our answer times 10 to the power of 2. Gives us 1.602. So at 0.04, we have 1.6. So 0.04, which is here. Just gonna trace it up. That's terrible trace. 1 second. 0.04. So this is 1.6 here. Okay. Now that's traced. Yes, that's fine. This is the value. Okay, so now here 0.04, right? This is double 0.08 is double of 0.04. As we said, when d, this is d, right? So d is getting doubled. That means delta y is getting halved. So what's 1.6 divided by 2? 0.8. So at 0.08 we have 0.8. Is this 0.8? 0.8 is here. So this is our point. Okay, and at 0.12, remember this means it got tripled, so we're gonna divide delta y by 3, right? So go back to your original answer of 1.6. 1.6 divided by 3, it's gonna give me 0.5333. So at 0.12, it's gonna give me 0.5. I'm not gonna use this, I don't need it in the marking scheme. So at 0.16, I'll just skip to 0.16. 1.6 divided by 4, because it got multiplied by 4, 0.4. So here, right? This is my graph. It's gonna look something like this. So forward sketch it. No, 1 second. Something like this, but let me just get the shape more accurate. This is good. Also, it's good. Okay, the graph would look much better on paper, but I'm doing it on tablet. So if I would start like this, this is good. Okay, this is a perfect graph that just got ruined by my Samsung Notes. Thank you. Okay, this is fine. This is fine enough. It does pass, right? It passes. Yes, it passes. Close enough. Okay, that's fine. Now, this is what your graph should look like. Now, the marks you get for this question, by the way, I fixed the graph a bit. That's why I paused the video. I fixed the graph a bit. This is what it should look like. The marks you get for this question is, first of all, it's a curved mark with a negative curved line with a negative gradient of decreasing magnitude throughout from slit separation 0.04 to 0.16. Yes, ours is a curved line. That's correct. Let me get the red pen. Curved line, and you are seeing that there is a decreasing magnitude, like basically the slope of the tangent is decreasing essentially. So that is also correct. Now, line of gradient ending at 0.16, comma 0.4. So 0.16, yes. 0.4, yes. So this is also correct. And the line has to pass through 0.08, comma 0.8. So 0.08. 0.08 and 0.8, that's correct, and 0.04 and 1.6. So 0.04 and 1.6, that's correct. Okay, yes, so we have full marks on this question. Now, as I said, I will do it using the other way. So if you did not understand this method, right, which is totally fine. This is a bit annoying for some people and some people won't get it. What you can do instead is you can just keep plugging in values. So remember, ym is gonna be m lambda d over d, right? Now, for simplest cases, we're gonna take m as 1. So again, it's gonna be delta y. Realistically, this is actually delta y, right? This is not, why is it making a right triangle? Let's make it normal, please. Okay, no, I don't want a right triangle. I don't want a right triangle. Okay, خلاص, delta y is now a right triangle. تمام. This is actually what we're gonna have to use. Okay, memorize it, please memorize it. If you want further, look in the file that I will put a link to in the description, where I actually solved the past paper. It's just a file of the past paper solved. Okay, it's my rough working, but it has the derivation of this, and it's very important. Okay, it's very important, you should note. You can always just plug in values, right? So 0.04. Now we have lambda, we have d. So lambda is what was it? 7.2 times 10 to the power of negative 7 times 0.89, right? Over 0.04 times 10 to the power of negative 6, or 10 to the power of negative 3. Okay, you get 0.16, whatever. You multiply it by 10 to the power of 2, because again, we get this in meters. Our value on the calculator right now is in meters, but you want it in centimeters. So times 10 to the power of 2. gives me 1.602. So 0.04, 1.6. That's fine. Now, we're gonna go back up to our, we're gonna press the up button to go back to our original equation, the one we did with lambda d and whatever. Instead of 0.04, we're gonna write 0.08. And then multiply that also by 10 to the power of 2, you will get 0.801. So 0.08 gives me 0.8, basically. Yeah, that's correct. That's fine, right? We're just plugging in values. Now, we're gonna go back up again, and we're gonna swap it with 0.12. So 0.12 times 10 to the power of 2 gives you 0.534, okay? 0.534. Now in the marking scheme, it's not a required point, so I don't know. It might be this. Genuinely, it looks like it is a correct point, yeah, because 5.3 isn't really something you can have on the scale. So yeah, this looks like it is possibly correct. Yes, we'll take it. We'll take it as an approximation. It's not required in the marking scheme. They don't expect you to graph it. Okay. So 0.16. Now, instead of 0.12, we're going to change it to 0.16. And then you know the thing, we're going to multiply it by 10 to the power of 2, 0.4005. So 0.16, 0.4. Done. That is all correct. So you have all the correct points here. So you have the correct point here, you have the correct point here, you have the correct point here, and you have the correct point here. They're all correct points. Okay. That was question 1. Now, question 2. State what is meant by diffraction. Diffraction. Sorry, why am I writing the fraction? It is the passing of a wave through an aperture. Memorize it as aperture. And the wave spreads into geometrical shadow. This will guarantee you the marks for this question. And again, it's 1 mark, so it's a free mark. Okay. A screen is parallel to the grating. Okay, so you have this light of wavelength. So this is the only part I need to know. 720, this is lambda. So lambda is equal to 720 times 10 to the power of negative 9 meters, right? Nano is 10 to the power of negative 9. Diffraction grating, this is another thing I need to know. Okay, now, a screen is parallel to the grating, an interference pattern is shown, and the angle between the angle between the second order maximum is 52 degrees. So first of all, what I'm gonna do is, I can't work like this, right? Because what is this? Hey, this is an angle between both maximums. I don't need that. What I need is the central maximum and the second order maximum. So this is actually gonna be a right triangle. What's 52 divided by 2 is 26 degrees. This is gonna be just, I don't know, I'm writing out all values. I forgot if I need this or not. 90 minus 26, 64 degrees. Okay. Calculate the frequency of the light. Now, immediately we should know V equals F lambda. V is actually in our case C, right? Because it's the speed of light. It's an electromagnetic wave. So C equals F lambda. Now, F is going to equal to C over lambda. So F is equal to 3 times 10 to the power of 8 over lambda, which we said was 720 times 10 to the power of negative 9. This gives me 3 times 10 to the power of 8 over 720 times 10 to the power of negative 9. 4.166 repeating hertz. So this we're gonna round to 4.2, sorry, times 10 to the power of 14 hertz. We're gonna round this to 4.2 times 10 to the power of 14 hertz. Okay, this is our answer for this question. Okay, now moving on, calculate the lines, the number of lines per unit. So we have an angle. So immediately, whenever you have an angle, you should always think of the formula d sine theta equals to m lambda. Okay, immediately think of it. Right, now, we have sine theta, we have m and lambda. We need to find d. Why will we find d? I'll tell you now. So d is going to equal to m lambda over sine theta, which is equal to, remember, m is 2 because it's the second order maximum. And that theta is going to be the angle between the central maximum and the second order maximum. So 2 times 720 times 10 to the power of negative 9 over sine 26 was the angle, 26 degrees. Now, do this on a calculator. 2 times 720 times 10 to the power of negative 9 over sine 26. Sorry, I forgot to close the bracket. 3.4 or 3.284 times 10 to the power of negative 6. Okay, now, for the sake of the A level, we're going to use this value. Okay, we're going to use this exact value. But, however, we're going to say in our working, because remember, the AS, the Cambridge, will only accept two significant figures. So, 3.3 times 10 to the power of negative 6. There are exceptions to the two significant figure rule. But for the most part, it is the case. Most of your answers will be reported to two significant figures. Okay, now, you have this, okay? You have this. What do you do with it now? This is in meters, okay? What you're gonna do is you're gonna have a formula, okay? It's N, the number of lines, is 1 over D. 1 meter, okay? This is 1 meter. Keep in mind. I'll use this data. I'll use this in another question. So, N is gonna equal to 1 over 3.3 times 10 to the power of negative 6. This is gonna equal to 1 over answer 304,000. We're gonna write 3.0 times 10 to the power of 5, and that is the answer. Okay, moving on. The light of figure 3.1 is now replaced with a light of a different wavelength lambda. It is observed that the third order maximum of this light are at the same position as the second order maximum of this in figure 6.1. Okay, so we're gonna use d sine theta equals m lambda. Again, why? Because they said they're at the same position, so they have the same angle, right? 26 degrees here. Said though, instead of this, it's gonna be third order maximum, right? So we want the wavelength lambda. Now, d is gonna stay the same, 3.3. Remember, we're using this d. This is d. 3.3 times 10 to the power of negative 6. So 3.3 times 10 to the power of negative 6 sine 26 degrees equals to 3 lambda. Because remember, m became 3. Now, doing this, 3.3, or actually lambda, because I'm not going to bother using the equation solver. This is easy to do without it. 3.3 times 10 to the power of negative 6 times sine 26 degrees over, what was that? Over 3. Now, do this on your calculator. 3.3 times 10 to the power of negative 6 times sine 26 over 3. 4.82. So lambda is equal to 4.82 times 10 to the power of negative 7 meters. However, look in the question what they want. They want it in nanometers. So what do? We're going to shift this twice. So we're going to have lambda is equal to 482 nanometers. Now, we're going to round our answer, because it's two significant figures, to 480 nanometers. And that's our final answer. Now, don't worry about this in the actual exam. In the marking scheme principles, it does say if the examiner can round your answer to the actual answer in the marking scheme, you're good. You're fine. Don't even worry about it. But just as a quick note, and just remember. Now, the third question. Two coherent forces x and y of microwaves of frequency 2.5 times 10 to the power of 10 hertz are a distance of 0.18 meters apart in a vacuum, as shown in figure 6.1. This is figure 6.1. Okay. There's a phase difference of 90 degrees between the waves emitted at the two sources. Okay, this is very, very, very important. So, phase difference is denoted by delta phi. Okay, you can also denote it like this, but I write my phi like this. They're both correct. Okay, so this is delta phi. Delta phi is equal to 90 degrees, just something we should know. A microwave detector moves along the line PQ, which is parallel to the line joining the two sources and 2.3 meters away from it. Okay, now, The detector is it here in the, no, it's not in the figure, that's fine. Point O on the line PQ is the position that's equidistant from the two sources. Point A is the position on line PQ where the intensity of the microwaves is the greatest. Okay, explain why the position of greatest intensity is not at point O. Now, normally, it would be at point O. It would be, this is the central maximum, but it's not. Why? Because of this, the phase difference. This is very, very important. So essentially got shifted 90 degrees. That's what that's saying. Okay, so what we're gonna write is there is a phase difference of 90 degrees at O. Right? That's the first mark. And then you have to say for, sorry, that was the way this for I've ever written. For maximum intensity the waves must be in phase. So phase difference has to be 0. Okay, that's what that's essentially saying. Now, on figure 6.1, draw a cross to show the position of the point on line PQ where the intensity minimum that's closest to point O occurs. Label this point B. Okay, now, the way I can explain this is by explaining what phase difference is. And the way I will explain what phase difference is by drawing two graphs. So, I'll draw the graph of X and the graph of Y, because remember, the two light sources are, if I can draw a straight line. Okay, there we go. So, this is the graph of the wave of X, right? I'm gonna take it like this. This is very much not to scale, okay? Or actually, this is better. This is gonna be X, okay? Now, this is gonna be Y, okay? So Y is gonna be something like this, okay? Or actually, let me, okay? Now, so here, what the phase difference is, it's the difference between the two maxima. So here's the maximum. Okay, so this is our phase difference. We're gonna call this value delta phi. Okay, this is the phase difference essentially. Look, you can see it's shifted. The graph is the same. Now, obviously my drawing is bad, but these two have the same maximum. Like these values are equal, right? The amplitude. So this has to match this. Okay, like my drawing is just terrible. Did I just erase the wave? Okay, my drawing is just terrible, but they have the same maximum. So the amplitude here matches the amplitude here. Okay, now we have this. Okay. So, when are the waves in phase? Okay, the waves in phase are in phase here, right? There is no phase difference. So this is A. Okay, now, okay, O is gonna be somewhere else. We're not gonna bother calculating it. Now, B is gonna be there where the other waves are in phase. Okay, but as you can see here, it says draw across show point B. What is point B that they say? The intensity minimum. So where they are. Okay, so I just decided to take the graph from Desmos because my graph was very long, and it wouldn't work well. So essentially, what this is saying here, right? Why am I on the pen? Okay, that's amazing. Here, point A, right? Point A is gonna lie it on, let me graph it, wait. So point A will be on this point here. Okay, this is point A. Okay, so wait, let me use the Samsung Notes one. This is A. Why? Because wave 1, okay, wave 1, which is the sine wave, right? Say wave 1 is the minimum, right? And wave 2, which is the cosine wave, because it's a shift, right? I'm not gonna get into the math behind it. Wave 2, okay, again, don't follow the math. I'm just putting it for your reference, is at 0. So we're going to obey the principle of superposition, right? The resultant intensity here will be a maximum, okay? Now, B, okay, B will be here. Because here wave 1, which is the sine wave, is at the maximum, and wave 2 is at the 0. So here the intensity will be a minimum, and O is, anyway, it's like an intersection, so you don't need to worry about it, right? Now what I'm concerned about is that OB and OA are at the same distance. From the graph you can tell that. So OB and OA, so let's say this is here, so then it's a bit longer. This is about the same, like this is about the same distance. So roughly the cross is gonna be here, right? Essentially, ignoring all of this, right? Ignoring all of this, don't follow this. This is honestly dumb of me to even include. Okay, OB and OE are at the same distance. Just memorize it if it comes, because the written is gonna come copy paste. Anyway, show that the length, the wavelength of the microwave is 0.012. So V equals F lambda, right? So lambda is equal to V over F. So lambda is equal to 3 times 10 to the power of 8 over, the frequency was given, how much was it? 2.5 times 10 to the power of 10. So over 2.5 times 10 to the power of 10. This gives you 0.012 meters, exactly. Okay. Now, for point A on line PQ, determine the differences in distances delta x traveled by the microwaves from X and the microwaves from Y. Okay, this is not hard at all, and it's actually very, very easy. So how would you do this, right? It's very simple. So we have our formula, delta x, sorry, we have our formula, delta x is equal to, we have multiple formulas for delta x, but we're actually just going to use one. We're going to use delta x is equal to delta phi over 360 over lambda. Okay, this is all in one fraction. Now, why are we using this? Actually, let me write it in the original equation, so then we can use it on an equation solver and it's much easier. Delta phi, sorry, that's not phi. Delta phi is equal to 360 over lambda times delta x. Okay, now this is our formula. Okay, we have delta phi. The reason we can't use L2 minus L1 or M lambda or whatever is because they're out of, they're not, how do I say this? Their phase difference is not 0. So it's a bit harder to calculate, so we're gonna have to be using this. Okay, this is the formula. Now, delta phi is 90 degrees, right? We know it. Equals 360 over lambda was 0.012, we just calculated it, times delta x. So on your equation solver, for your calculator, you're gonna put 90 is equal to 360 over 0.012 times x. 3 times 10 to the power of negative 3, which is the answer. So delta x is equal to 0.0030 meters. Done. Okay, now use the formula for the double slit interference of light to calculate the distance between adjacent intensity maximum. Okay, so this is again adjacent intensity maximum means adjacent bright fringes. So what are we going to use? We're going to use the delta y formula. Delta y is equal to lambda d over d. Now here they're actually telling you use the double slit formula, so we're gonna have to use this one. Ym equals m lambda d over d, right? So it's gonna be y2 minus y1, right? Because they're adjacent, so it's the first bright fringe minus the second bright fringe, or the other way around, you know what I mean, right? This is gonna equal delta y, but I'm not gonna derive delta y. As I said, you see how I derived it in the file. Now please look at it, by the way, genuinely please do look at it. So 2 times 10 to the power, 2 times 0.012 times 2.3, because remember capital D is 2.3 meters, okay, and then small d is 0.18 meters, so over 0.18, okay, this is gonna equal to y2, so this gives me 2 times 0.012 times 2.3 over 0.18. 0.36666 repeating. Okay, this is meters. Now, y1 is equal to 1 times 0.12 times 0.012 minus 2.3, or sorry, times 2.3 over 0.18. So this is gonna equal to 0.15333 meters. Subtract the two, so 0.36666 minus 0.15, minus the answer, just to be careful. So you're gonna get delta, the path difference, because that's what they want, or the distance between the two, d, or we're not gonna do that, we're just gonna write y2. I can write properly. Oh my god, y2 minus y1 is equal to 0.153, or we're gonna short for working 0.306666 minus 0.15333. Okay, this is gonna equal to 0.15333 repeating. So we're gonna round to two significant figures, 0.15 meters. Done. Now, light of a single frequency is incident normally on diffraction grating. Okay, diffraction grating, this is what I need to know from this question. This sentence, sorry. Why is it drawing triangles? So you can tell today I'm not, the brightest. So the light has a wavelength of 520 nanometers. This is lambda. Okay, the separation of the lines in the grating is this. This is d, small d. Okay, now determine the total number of bright fringes formed on the screen. So total number of bright fringes means the maximum, actually, if you think about it, right? It's the maximum number of bright fringes that can form. So we're going to use the formula d sine theta, because I'm lambda. Why? Because this will give me m. M is going to have the maximum number of bright fringes on one side. You'll see what I mean later. So if you want the maximum, this sine value has to be the maximum, right? So what value of theta will give me the maximum sine value? If you know, if you sketch the graph, okay, for the sine graph, you know that it peaks at 1, right? So sine theta is equal to 1. Do the inverse, you're gonna get theta equals 90 degrees, and you should know this by heart anyway. So we're gonna do d, which is, we have it given. Why am I doing that? 3.8 times 10 to the power of negative 6 sine 90 is gonna equal to m times 520 times 10 to the power of negative 9. Okay, now this is gonna give me 3.8 times 10 to the power of negative 6 times sine 90 over 520 times 10 to the power of negative 9. 7.3. So m is equal to 7.3. Obviously, you can't have 7.3 bright fringes, right? It's either you have a bright fringe or you don't. It's a whole number. So we're gonna round 7 bright fringes. Now, because it's only 90 degrees, right? Look, it's 90 degrees, so it's gonna be 7 up, right? It's only 7 up, but you're forgetting that we also have the down. We always have the down and the central maximum. So then you have one in the middle, one bright fringe in the middle, the central maximum, and 7 down, right? Because if you have up, you're gonna have down. So add them all up. You're gonna have 7 times 2 plus 1. 14, 15. 15 bright fringes, right? 7 plus 7, 14 plus 1, 15. 15 bright fringes. Okay. The light is replaced with red light of a single frequency. State whether the frequency of the is original light. Okay, so how much you have to memorize the color spectrum. Red light has a shorter frequency because this is gonna give me a very high frequency. Let me calculate the frequency of this. So 3 times 10 to the power of 8 over 520 times 10 to the power of negative 9. Okay, this gives me 5.76 times 10 to the power of 14. Okay, now the frequency of red light, okay, is approximately I forgot it. Okay, the frequency of red light, I remembered it. It's about 4.3 times 10 to the power of 14. Okay, please memorize the spectrum. So, you calculated 5.7 times 10 to the power of 14. Red is 4.3, so obviously it's less. Right? You get a mark. That's your mark. Now, State and explain the effect of this change on the number of bright fringes formed on the screen. A calculation is not required. Okay, so since you have less bright fringes. Oh wait, no, this is the answer. Let me explain why. There's less bright fringes formed. Why? Because remember the formula d sine theta equals m lambda, right? Now we're not changing theta. We're not changing d. We're only changing lambda, right? So m is what we want to know. Okay, so I'm gonna bring this back, d sine theta. Now if lambda increases, right? So you're gonna have d sine theta with a bigger lambda, right? So the ratio of this to this is gonna be smaller, right? Because for example, 5 over 2, 2.5, right? But 5 over 4, this is what? This is, I think 1.2, right? 1.25. Look, if the number here increases, look, you get a smaller fraction, right? So since it's increased, right, we're gonna have a smaller value of m. So m will decrease, because as you can see, m and lambda are inversely proportional. Look, as m decreases, lambda will increase, and as lambda increases, m will decrease. So because they're inversely proportional. Less bright fringes, the marking scheme literally will only say less bright fringes as wavelength increased. But if you want the full explanation, you can write the inversely proportional. So these are the calculations not required. Okay, what page are we on? We're still on the 9th. Wow, okay, we have a lot to go, and we're almost an hour in. So, electromagnetic wave, it's electromagnetic spectrum. You should memorize the ranges. Infrared. Okay, state the frequency. V equals F lambda. F is equal to V over lambda. So that means F is equal to 3 times 10 to the power of 8 over lambda, which is 8.4 times 10 to the power of negative 6. Lambda is given here. Okay, so this gives me 3.57 times 10 to the power of 13. Okay, now here they're telling you in terahertz. T hertz means tera. Now I'll give you a trick for memorizing it. So you have the meter, you have nothing, you have here nothing, right? You have the kilo, the mega, the giga, and then the tera. Okay, this is times 10 to the power of 3 times 10 to the power of 6 times 10 to the power of 9 times 10 to the power of 12. You can see they're increasing by 3, right? So I only know till mega, but I know they increase till by 3. So you can easily figure it out. Now here they want it in terahertz. We have times 10 to the power of 13. So what are we going to do? We're going to shift it 1. So it's going to be 35.7 times 10 to the power of 12, which makes it 35.7 terahertz. But again, they accept 2 significant figures. So it's going to be 36 terahertz. Okay. This is something similar to the other question we did, the first question. So an arrangement that uses a double slit to demonstrate the interference of light from a laser is shown in figure 5.1. So this is figure 5.1. This is capital D. This is A is the small d. Okay, this is the wavelength lambda. Okay, now we have this. Okay, so we have this setup. I'm not going to read all of this because I already read it. It's fine. And then they're telling us this is the pattern that's got formed on the screen. I don't need to read anything else. The light waves emerging from 2 slits are coherent. Coherent, again, same nature. Constant phase difference. Calculate the separation A of the slits. Okay, so we're going to use Ym equals M lambda D over D. Okay, this is instead of D we're gonna write A. Okay, because they have it given to us as A. Now we're gonna use this, and we're gonna use the delta Y. I know I keep using it a lot, but it's genuinely very, very, very important. Okay, I even use it in the file, and again I use it a lot, and it's for a good reason. But I'm not sure we can use it. We're gonna avoid it because for the sake of the video, I'm gonna avoid it. I'm gonna try not to use it. So let's label. So we have the first. So this is, they told us these are the bright fringes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bright fringes. Okay, now I can't take this, but again, it's gonna be relative to my calculation, so it's fine. Like I can take this as 4, it's fine. My calculations will not have an effect. It's fine. You'll see what I mean now. Okay, so now the dark fringes, so we're gonna take it from here. We're gonna start taking it from here. So actually it's just 0.5, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5, 8.5, 9.5, and we don't need the 10.5 house, we're good here. Actually, we don't even need those. We're done. Okay, now we're gonna find the distance from the 10th bright fringe and the second bright fringe. So y10 minus y2, this will give me 9 lambda d over d minus 2 lambda d, or 10 lambda d minus 2 lambda d over d. This is just going to equal 8 lambda d over d. And how much is this equal to? 22 millimeter. So 22 times 10 to the power of negative 3 meter. Right, we have lambda, we have d, we want to find this. So we're going to swap this with a, I said I will. Okay, now 8 times, what was lambda? Lambda was given 6.2 times 10 to the power of negative 7 times 6.2 times 10 to the power of negative 7 times, I think d was 2.8, I'm pretty sure 2.8 over a, over a is equal to 22 times 10 to the power of negative 3. Now, do this on a calculator. So, 22 times 10 to the power of negative 3 over 8 times 6.2 times 10 to the power of negative 7 times 28, or 2.8, sorry. Gives me a as, this is wrong. This can't be correct. What did I do here? 1 second. Oh, okay. I know what I did. So what I actually did, I flipped the calculation, right? This is why you have an equation solver, but it's fine. So what you're actually going to do is 8 times 6.2 times 10 to the power of 7 times 2.8 over 22 times 10 to the power of negative 3. This will actually give you the correct number, which is a is equal to 6.3 times 10 to the power of negative 4 meter. Wait, what? How did I get 10 on my calculator? 1 second. I got the right number. Did I do something wrong? Wait, again? Yes, I did something wrong. Again, I put times 10 to the power of 7, negative 7. There we go. 6.3 times 10 to the power of negative 4. So, just do this on an equation solver, as you can see, and you know, خلاص. Again, I'm not the brightest today. No, I'm not in a good mood. So, here. Fringe P is the central bright fringe of the interference pattern in B. Fringe Q and fringe R are the nearest dark fringe and nearest bright fringe respectively to fringe P, to the right of fringe P, as shown in figure 5.2. Calculate the difference in distances. Okay. So, we're going to use the formula. They set path difference. So, we're going to say delta equals m lambda. Okay. Now, here, what do we have? We have P and R. So this is going to be m equals 6 and m equals 5, right? Because we're caring about the relative to Q. So, 6 lambda minus 5 lambda, right? M equals 6 and m equals 5. That's what we said. Because look, they want it here. It's they said calculate the distances from each slit to the center of Q, right? So finding this, by the way, m equals 6 minus m equals 5, you know what this will give us? This will find the distance from P to R, right? But we're gonna then divide that by 2 to find P to Q, and then it's gonna be the same difference as Q to R. So finding this, the 6 lambda minus 5 lambda is just lambda, right? Lambda is equal to 6.2 times 10 to the power of negative 7. Now, this is the difference, this is the distance from P to R, right? As I said. Because look, we're finding the path difference. The path difference, we found the m equals 6 and m equals 5. So we found the path difference between P and R. right? But what do they want? They want from P to Q and from R to Q. They said from each slit to Q. So from here and here, from each fringe to Q, sorry. So we're gonna divide this by 2. We're gonna divide the lambda by 2. So do it with me. 6.2 times 10 to the power of negative 7 over 2. 3.1 times 10 to the power of negative 7. Okay, now the phase difference, you're gonna find that delta phi is equal to 360 over lambda times delta. Okay, now delta phi is equal to 360 over 6.2 times 10 to the power of negative 7 times, remember what we found as delta? This was delta 6.2 times 10 to the power of negative 7, right? Because that's the path difference. So the path difference is going to be 6.2 times 10 to the power of negative 7. Because look what we found. We found that delta is equal to m lambda, right? So this is delta. Delta is equal to lambda. Okay, what we found here in this part is the difference in the distances from the dark fringe to the bright fringe. No, they want it between R. So this is the actual delta. This is the actual delta that we just divided by 2 in the other question. This will give us, since these two will cancel out, 360 degrees. Okay, question, another question. This is just all, yeah, I'll read it later. State what's meant by coherent. I've said it 3 times now. I'm not gonna, you can look back. Difference in path length, so delta is equal to, what do we have? We have a double slit. Okay, I have small d, I have big D, I have lambda. Okay, now they want them at R, superposing at R. Okay, so R is here, right? So this is the central bright fringe, this is 0. The dark fringe is going to be 0.5, the bright fringe is going to be 1, the dark fringe is going to be 1.5, right? So R is M at R, so MR is equal to 1.5. That means we can use this. Delta equals to m lambda. That means delta is equal to 1.5 times, what's lambda? 660 nanometers, so 660 times 10 to the power of negative 9. This equals to 1.5 times 660 times 10 to the power of negative 9. 9.9 times 10 to the power of negative 7. However, okay, this value that you find, okay, delta here, this is 9.9 times 10 to the power of negative 7 meters. They want it in nanometers. So what you're going to do, you're going to shift the decimal point twice. So it's going to be 990 nanometers. Done. Okay, their phase difference, you're going to use the formula. Delta phi is equal to 360 over lambda times delta. Okay, now, since you have delta, you have lambda. This is very, very easy. 360 over lambda was 660 times 10 to the power of negative 9 times, what was it? 990 times 10 to the power of negative 9. This gives you 360. Sorry, where am I? 360 times over 660 times 10 to the power of negative 9 times 990 times 10 to the power of negative 9. This gives you 540 degrees. Done. Okay. Calculate the distance OQ. So what's OQ? OQ is this. This is OQ. Okay. So OQ, you're gonna use again the here. So it's from y0 to y of 1, right? So we're gonna write y1 minus y0 will give you the distance from O to Q. Right, y0 is going to be 0, right? Because you're going to have 0 lambda d over d, and then 0 multiplied by anything cancels out, so 0. So this is just going to go. So y1 is going to equal to OQ. So 1 times lambda times d over d will give me OQ. Right? Because remember, the formula is ym equals m lambda d over d. Right? So when m is equal to 1, it's just going to be lambda d over d. Right, so 660 times 10 to the power of negative 9 times times 1.8, sorry, capital D is 1.8. You can see it here. Okay, over small d, which is 0.44 times 10 to the power of negative 3. Okay, that's the distance in the slits here. Since it's in millimeters, we do times 10 to the power of negative 3. This will give you 2.7 times 10 to the power of negative 3 meters. Okay, now the intensity of the light incident on the double slit is increased without changing the frequency. Without changing the frequency, that means literally nothing changed in like relative to the position. Okay, the position will stay the same. So we're gonna write same separation between the slits. Okay, and then we're also gonna write, since the intensity increased, right, you can see that it got brighter. So the bright fringes are brighter. Now, there's also one more change, right? Actually, it's not even a change. There's nothing else changed. But they told you discuss the appearance of the fringes. That includes the bright and the dark. Now, realistically, since the thing increased, the intensity increased, the intensity, not anything else is increasing. Do you think that the dark fringes will have will change anything? Will like be changed? No, because intensity just means it got brighter, essentially, right? The light is stronger, right? So when it's something that's already dark, when there's like destructive superposition, right? Nothing. There is no difference, right? Because the dark fringes stay the same. Okay, because again, it just means the light got stronger. Yani bright fringes are still gonna stay, or dark fringes are still gonna stay dark, right? Nothing's gonna change. And no, because we know that you're gonna have bright fringes and dark fringes. If the intensity of the light increases, does that mean the dark fringes are gonna get brighter? That doesn't really make sense. They're called dark fringes for a reason. So these are the 3 marks. Now, light of 660 nanometers is now replaced by blue light. Okay. Since blue light, I'll just tell it to you from now. Please memorize the spectrum of the colors, by the way. Blue light has a shorter wavelength. Okay, this is just a fact. Okay, now, before I answer, I'm gonna write the formula. Ym equals m lambda d over d. Right, they want you to tell me if any change must be made to the separation. So they want this. Now, so since lambda increased, right? Or sorry, lambda decreased, right? That means that the separation also has to decrease, right? So in order to maintain this has to stay the same. This, they said, the separation, the fringe separation has to stay the same. So this has to have no change. That means since these two are directly proportional, right? When one decreases, the other has to decrease. So separation between the slits, look, separation of the two slits must decrease in order for the fringe separation to remain the same. Okay, I believe we have 2 more questions or 3 more questions, something like that. Yeah, we're almost done. Okay. Are we not done? Oh, this is another question. A laser emits a beam of electromagnetic waves. Okay, show that the wavelength. So V equals F lambda. Okay, lambda is gonna equal to V over F, which is equal to 3 times 10 to the power of 8 over 3.7 times 10 to the power of 15. This is gonna equal to 8.1 times 10 to the power of negative 8 meters. Done. Okay. Now, moving on. State the region of the electromagnetic spectrum to these. Okay, so the wavelength is this. You should memorize the electromagnetic spectrum. This is ultraviolet. Okay, this is the same concept as this question, this part. Wait, here, same concept. Okay, so they're basically telling you that this detector moves 180 degrees across this path. okay? And this detector detects the light. Now they want you to detect they want you to find the number of maxima that will the detector will detect. So we have the diffraction grating has 2400 lines per millimeter. This is n. Okay, now recall the formula for n is equal to 1 over d, 1 meter over d. They give us 1 millimeter, so this means 1 millimeter, change it to meters. So it's going to be 1 times 10 to the power of negative 3 meters over 2400, because that's how much lines they told us. Sorry, this was n. Okay, so d is going to be 0.001 over 2400. Okay, sorry, this is gonna be d. 4.16. 4.16. Can I just keep it? I think yeah, that's fine. 4.166 repeating times 10 to the power negative 7 meters. Okay, now we're gonna use d sine theta equals m lambda. Okay, so we have d 4.1666 repeating times 10 to the power negative 7. Sine. Now, it says it moves 180, but that's a trick, because to sine 180 would give you 0. And then you'll be confused, oh, what do I do? What do I do? We're going to say sine 90, because sine 90, that means like this. Take it as 180 is 2 times 90, right? So it goes 90 degrees twice. So it's going to go here, okay, stop here, then going to go here. Okay, that's essentially what 2 sine 90 is. So sine 90 is going to equal to m times the wavelength, which we found was 8.1 times 10 to the power of negative 8. So times 8.1 times 10 to the power of negative 8. Okay, now do this on your calculator. So 4.1666, I think I have the answer here. Answer sine 90 over 8.1 times 10 to the power of negative 8. M is equal to 5.1 bright fringes. However, you can't have m as 5.1, right? You have to round down, because you always have to round down, even if it's 5.999. Always round down. So this is gonna be 5 bright fringes. Now remember, it moved on 80 degrees. This is how much in 90 degrees. So that means it moved. That's gonna be basically 5 bright fringes up, then 5 bright fringes down, right? But then you're forgetting also about the central maximum. So there's 1 here. So it's 5 times 2 plus 1. Okay, if you want to know the formula for the thing, it's basically m times 2 plus 1. This is the formula. M is 5 in our case, so it's going to be 11 bright fringes, or 11 maxima. Now, the light is now replaced with one that emits electromagnetic waves of a wavelength of 300 nanometers. Now, 300 nanometers times 10 to the power negative 9. They gave us 8.1 times 10 to the power negative 8. We're comparing lambdas, right? So this is lambda 1, this is lambda 2. So what we're going to do is we're going to take it back. So this is equal to 30 times 10 to the power negative 8. So you can see that the wavelength increased. So longer wavelength. So less maxima. Why? Because if you use d sine theta equals m lambda, because they're asking about the number of maxima now detected, right? Lambda increased, right? So again, the ratio of d sine theta to lambda is gonna decrease, and the value of m is just gonna decrease because lambda increased. They're inversely proportional, as you can see. So the longer wavelength, so less maxima detected. Done. Okay, last question. State the principle of superposition. I stated it twice. 2 waves with intensities for. Okay, this one I'm not sure if it's gonna come, but memorize it. It's a very easy formula. The intensity is inversely proportional to the square of the amplitude. Now write down the words intensity and amplitude. Sorry, did I say inversely? Directly proportional. Okay. So that means that the first one, the intensity of the first light is just going to be radical I, right? And then the intensity of the second is going to be radical 4I, right? Which is equal to, because I have I and 4I here, it's equal to 2 radical I, right? So that means add them up, the total amplitude is going to be 3 radical I, right? Because this is 1 radical I. 1 radical I plus 2 radical I, 3 radical I. Now, remember, we said that the intensity is directly proportional to the square of the amplitude. So we're going to square this. So the intensity is going to equal to 3 radical I squared. This is going to equal to 9I. Now, keep in mind, they said, why did I add them? Because it said maximum possible. So that means ideally constructive, like the maximum destructive. If they said minimum, I would subtract this. I'd subtract A2 from A1 and then I'd square it. Okay, but here it said maximum. That means it's constructive interference, not destructive. Okay, so 9 is my answer because of that formula. However, I don't think this is coming. I wouldn't count on it. Now, I just have this too. Okay, كوهنت خلاص, I don't need to read this. I need this is my lambda. This is my small d. This is my capital D. Okay, what do they want? They want the distance between the centers. So they want, for example, y2 minus y1. Okay, so this is gonna give me delta y, which is lambda d over d. Okay, this is delta y. Okay, I'm gonna solve it using this. So, or I don't even need it. Again, I said you can do y2 minus y1, right? So you're gonna have 2 lambda d over d minus 1 lambda d over d. Subtract, so 2 lambda d minus 1 lambda d, it's gonna be lambda d over d. And essentially, this is the derivation of delta y. I just did it essentially, right? Because when it's adjacent, they're next to each other. So 2 minus 1 is 1. This is why delta y is this. This is why this is delta y. This is its derivation. Okay. The actual derivation is a bit different, but it's the same concept. This is the same concept. So that means that we have lambda, we have capital D, and we have small d. So all we have to do is apply. That means 550 times 10 to the power of negative 9 times 1.2 all over 0.35 times 10 to the power of negative 3. This gives you 1.9. We're gonna round it. 1.88. 1.9 times 10 to the power of negative 3 meters. Done. Okay. Now, light is replaced with the red light. I told you red light will have a shorter wavelength than this. So, or wait, no. Red light will have a shorter frequency than whatever this is. So, longer wavelength. Okay, so that means they want the distance in the centers, right? They want to see if it has a change in the distance. Lambda will increase, right? Lambda will increase. So that means, and they said everything is kept the same. They didn't say anything about anything else. They all just changed lambda. So this is the same. This is the same. That means that delta y, which is the distance between the centers, is gonna increase. So distance between centers of bright fringes increases. But this is the end of the past papers. I hope you learned, or I hope you enjoyed. Good luck, everyone. And before I go, I want to shout out to people. One asked me last video and I forgot to. I'd like to shout out Dani, and I'd like to shout out Jamil Aql. Yalla, thank you حبيبي. Bye.